I'm Dr. Narsinga, Professor of Physics, Dean Research and Development, Marri Reddy Institute of Technology and Management. Today we will study about lab experiments that is related to Hall effect. So this Hall effect is nothing but if the material, that is current carrying semiconductor or conductor, if we keep in a magnetic field, so there is a voltage will be induced. That voltage we call it as a Hall voltage. This total phenomenon we call it as a Hall effect. That means if any material, that means it's a maybe semiconductor or conductor, if the current carrying conductor, that means if you send the current through that material, if we keep that material into magnetic field, then voltage will induce without any changing current. That means if this current, voltage and magnetic field will be perpendicular to each other. So that means the diagram you can see here, there is a material, this rectangular bar is a material. So we are sending current through this along the x-axis direction. So then along the y-axis we are sending the magnetic field. That means it will be north pole and south pole. It will be in terms of thickness. Then there will be voltage will be induced in another direction. That means these three are perpendicular to each other. So if it is current in a x-axis, the magnetic field will be in y-axis, and voltage, induced voltage will be in the z-axis. These are the three different directions that is perpendicular to each other, these three parameters. So this phenomenon discovered by Edwin Hall in 1879, that is very old phenomena, that is 1879. Later on there is a different type of quantum with a nanoparticle, that is a quantum effect is came into picture. After that the quantum Hall effect also discovered, that is around 1975. But before that it will be Hall effect only. That Hall effect is 1879, Edwin Hall. In the name of his scientist name, this experiment is called as a Hall effect. Okay, going into experimental things. So there is a aim of the experiment. Usually any lab experiment, we have there is a some aim, how what we have to do. So that means to determine the Hall coefficient of a given semiconductor. So in a given semiconductor, we have to calculate the Hall coefficient. So using this Hall effect, that is a experiment, lab experiment. Okay. So it has a Hall effect panel. This panel contains the sample and like a 4-probe method they use along the x-axis, y-axis. We will use along the x-axis we use current, and at y-axis it will be voltage. So that means the voltage current will be perpendicular to each other. In the thickness direction there is a magnetic field. So these three are perpendicular to each other. So that means it requires a Hall effect panel, that is a sample holder, Hall probe, electromagnets we required to send the magnetic field, then constant current power supply. That means we have to send some voltage or current. It should be constant one. So then there is a digital gas meter to measure the magnetic field, how much magnetic field at that sample place. So it requires some Hall probe. This Hall probe is working in a phenomenon of piezoelectric effect. That is small things will be there. You can see in the experiment there is a different type of means apparatus are there. There is a Hall probe stand. So there is a stand, that is a metal stand. If it is iron stand, then the magnetic will be attract. That's why they use usually in a means wooden stand. So this Hall probe, it contains the small like a plate like things will be there, that is a red color. So these these two blocks are electromagnets. If you send the current, there is a magnetic field will be induced. That magnetic field, it will be measured by this gas meter. So that is gas meter, it will measure directly how much it will be magnetic field with this current. So you can see here there is a 1 amp current they send through this some electromagnets. You are getting 0.1482. These are the in terms of Tesla. Actually in our experiment in laboratories usually it will be in terms of kilogas, but here the experiment, this experiment is in terms of Tesla. So kilogas and Tesla, it will be only Tesla means it will be 10 to the power of 4 gas. So whereas in kilogauss means it will be 10 to the power of 3 kilogauss, 10 to the power of 3 gauss. So that means if 10 kilogauss, we can say it will be Tesla. That is another parameter where is just symbol, that is we can say it will be Tesla in terms of 10 to the power of 4 gauss. So this is the actual experimental. This is only for measuring the magnetic field. Okay, this one. So then we can replace this probe, that is Hall probe. It will be replaced with sample holder. So usually the sample holder will be like this. So it will be the sample will be through thickness, the north and south pole. This is the electromagnets. So we will send the electromagnetic field along the thickness direction. So remaining, that means the length and width, we will measure the length, we will send the current, then we will measure the voltage here, that is a width direction. So this is a magnetic field direction, that is inside it will be the thickness one. So this is a sample. You can see here there is a 4 contacts. One is along the length direction, another 2 is the width direction. So already we measured that magnetic field using that Hall probe. So here we use the same, that what we are getting in 1 amp, we are getting 0.1482 Tesla. Na? So that one we use here only one, that's we measured one table with current versus magnetic field. Then we replace, that means we are not changing any position of these electromagnets. So that means whatever the current we are sending, we assume that it will be same magnetic field will induce without, because we are not changing any direction or position of these electromagnets. So that's why we will say it's a 1 amp current, this one maybe 2 amp current, it may be 0.28 or something Tesla. So like that it will be vary. So that variation we will note down first. That means 0.5 amps, 1 amp, 1.5 amp, 2 amp, 2.53, like that. So we will go around 3 amps only, not very high, because amp current is very high current. So we use only around 3 amps current. So then we just take one table of this one, that is magnetic field versus current. Then that same current we use for this sample. So we are sending some means current, that is 0.5 milliamps current. Then we will get some voltage. So that voltage, the current will be constant. The voltage will be vary with this current. That current means nothing but magnetic field direction. So that means the magnetic field vary. So that voltage will be induced. It will increase. So voltage will be increases without changing the current. If the current change, voltage means that will be normal Ohm's law, if V is equal to IR. So that's not correct. So here the current will be constant. We change only magnetic field. So because of that magnetic field, the voltage will be induced. This because of this voltage induced, we will get that effect. We call it as a Hall effect. So usually what happen in a sample, if you are applying the magnetic field and current means the electric field. This electric field, if you apply the electric field, the electrons will move is a normal places. That means along the field direction. That means if it is a field is like this, that is electric field, and electrons will move opposite direction, it will be in a straight path. If we are applying the magnetic field in this direction, so the magnetic field and electric field is means equalized. That means at thermal equilibrium position. That means magnetic field and electric field is equal. So then what will happen? The electron path will be moving. The path will change. So earlier, before magnetic field, the electron path will be along the field opposite to the field direction. But if you apply the magnetic field, that magnetic field is equilibrium to electric field, then the path of the electrons will disperse. That means it will move along the other direction. That means it will move the lower direction. That means the electrons or holes will move the lower direction. So how the voltage will be induced? Because in a lower position, we are concentration of carrier concentrates. That means the electrons are holes. Because the path of electron movement will be dispersed. That dispersion will be lower direction. So that because of that, these electron difference, so down plate it will be more electrons, upper one less electrons. So that means there will be carrier dispersion. So because of that, we will get the potential difference. That potential difference is nothing but voltage. So because of that, the voltage will be induced while we are sending the magnetic field. If your magnetic field is more, the induced voltage also increases. So in this way, so how we will measure those things, we will study here. So this experiment looks to be like this, but yeah, the principle is same what I told. If it is electric field and magnetic field is means equal, mutually perpendicular forces on that electron, it will be acting, the electron path will be dispersed. So there is a equation, so that equation, that is electric current. So that electric field is nothing but that's R into J into H. This small derivation is there when equilibrium positions are appears. That means the equilibrium position where the electric field is equal to electric field and magnetic force due to magnetic force. This is due to electric force acting on the electron is equal to 0. So this equation if you solving this equation, we will get like this one. So then there is a finally the constant term, that is RH, we call it as a Hall coefficient. Hall coefficient is nothing but it depends on the sample thickness and the voltage, induced voltage, how much induced the voltage will be. dVH, VH we call it as a, D is the sample thickness, VH is the Hall voltage, divided by how much magnetic field we are sending through that sample, that is magnetic field, then how much current you are sending through sample, that is I. So these using these parameters, we can calculate the Hall coefficient. So here what we are measuring, we are sending the magnetic field through the sample, as well as we are sending current also, constant current. Then we are the voltage is inducing. So we are measuring voltage, sending through current as well as magnetic field, we are measuring voltage. So with these three parameters, how we can calculate this RH value, I will show you. So this similar same equation where this what I draw here, it may not be clear. So now you can see there is a magnetic field direction along the thickness. So then there is a length direction, we are sending the current. In width direction, we are measuring the whole voltage. It requires the current, magnetic field, and thickness of the sample, and how much voltage is induced using this experiment. So if in a laboratory, it looks to be like this. Okay. So there is a gas meter is there. This is a power supply where we will send that leads to the current, this electromagnets. If you send the current, the magnetic field will be induced. That magnetic field induced, we can measure here. This is the gas meter. This one is the power supply. Okay. High power supply. It will be sending through these electromagnets. Then it's actually we are not noting this current actually, but some purpose we are measuring current, but this is not calculating for Hall coefficient, it is not useful. Okay, only to generate the magnetic field it will be useful. So that magnetic field will be here. This one, there is a two buttons will be there, we can it will be voltage as well as current. So first we can send constant current, then the voltage will be induced. How it will be induced, we can measure the same meter. Here this one will voltage as well as current. So we will send the current, then measure the voltage. That's depends on only these buttons. Okay. So that in some experiments there is a 2 meters will be there. One is voltmeter, another one is ammeter. So this experimental setup. Then how we can measure? First, actually, if you are any electromagnets, there is a some magnetic field will be there. That magnetic field means if we are using earlier one, okay, if you are using this, let us take it as electromagnets. If you use some higher magnetic field we generated through these coils, then that magnetic field may not be reduced to 0, because there will be, so there is a sudden switch off that power supply, or some experimental errors will be there. Due to that, there will be some induced magnetic field will be inside, it will be there. So that induced magnetization, if you want to reduce that, we call it as a demagnetizing the coils. Demagnetize means if some value is there, plus 1 kilogas or 10 gas. 10 gas also more actually in some experiments, but in Hall effect it may not be that much effect, but still we have to demagnetize. For that demagnetization, we have to reduce that current and increase. That means if you increase just 0.1 amp current positive, then once again reduce to minus 0.1 also. So that means if you change that polarity, that means north pole and south pole to north pole to south pole, so you will get that magnetization will be demagnetized. So then it will, you can see in that meter, that gas meter, if you see that zero count, then it will be, it already demagnetized. So if no current is passing through that electromagnets, you won't get any magnetic field. So that's the basic idea. First you start that experiment before start going to your real data. So you have to make sure there will be demagnetized that magnets, okay, electromagnets. Then we can switch on or off, that's a power supply, okay, there is a regulated power supply. So that means before going to start, to that magnetic course will be inside the knobs, so we have to reduce that knob. That means if there is any demagnetized value is not going zero, so there is a possibility, there is a one knob will be there to zero setter. So you can make that zero setter also, okay, to make sure that every reading will be proper. So then there is a sample holder we will keep, that that will be in a PCB. Like a PCB is there, there is a four wires will be there. So here it will be the sample, it will be rectangular bar. So these two, it will be connected to voltage one. These two, it will be connected to current one. So like that, there is a PCB is available, that sample holder will be available. We can change, if you want, you can change this sample. There is a some screw arrangement will be there, so that we can reduce that sample. If you replace that sample, you can use another sample also. That is a sample holder one. Then how we will, what are the steps we have to make, okay. So now we have to switch on that all the meters, like a gas meter, power supply, and voltmeter, ammeter, all these four meters we have to make on. Then there is a already we adjusted that one is a zero, that's a gas meter. Then you just small, initially you change the current, there is a small current you are changing, that is across the crystal, that means the sample. The sample we are sending around 1 milliamp current, that means at 1 milliamp current, what is the voltage? See, it depends on the sample. Some materials it will show very high values, that is conductors, but it is a semiconductor, so you will get 1 milliamp, maybe 30 or 40 millivolts you are getting. So this is without magnetic field, B is equal to 0. Okay. So if we are changing the magnetic field, if B is equal to 0 instead of B is equal to 0, then you change into 0.25 kilogas. What will happen here? Here it will be increases, this may be 30 to 33 millivolts, but current will be same. The current sending through sample, it will be same current. Only we are sending the magnetic field current, it will be increases, but the magnetic field also increases. So that magnetic field increasing, then we are getting more voltage. Similarly, if it is a 0.5 kilogas, then the this voltage will be induced maybe around 39 millivolts, like that. Okay. So that is a 39 millivolts, but current will be same 1 milliamp current only, but 30 to 39, that means 9 millivolts it is increased while increasing 0.5 kilogas. Okay. So that means it will be Hall effect will be induced that voltage with a magnetic field. So applying current to electromagnet, this one. So this is a one method where the constant current will be there. Okay. In some people we will measure in another way also, like the magnetic field we will be it will be constant magnetic field. We vary the current. That means 1 milliamp and 1.5 milliamps, 2 milliamps, like that. So we vary the current, then measure the voltage. This also voltage also induced actually. If you are if you want to check properly, so you just switch off that magnets, then measure current and voltage characteristics. That means if you send the current, voltage will be there. So how it will be vary? So you can compare with magnetic field, without magnetic field. You can see very clearly there is a difference. So we can calculate according to that also how our Hall effect will be induced that voltage. So then it will be, that is a variation of current as well as magnetic field. We can measure in both cases. So current constant or magnetic field constant. So we can measure in both ways. So how we can calculate these calculations? Once we calculate that Hall voltage versus magnetic field, then we can plot the graph. From that graph, we can take the slope. So that slope into thickness of the sample divided by I, you will get the Hall coefficient, because slope will be voltage versus magnetic field. So voltage versus magnetic field, we draw the graph. Because of that, the slope will be VH by B. So then the slope into D divided by I, you will get the Hall coefficient. Okay, Hall coefficient, usually that what I mean is units is a centimeter cube for coulomb. Is units of Hall coefficient. So in that way, so we will draw the curves. How we can draw the curves, I will show you. That's actually, you can see here, there is a magnetic field in terms of there is a constant magnetic field here, that is 0.1482 Tesla or 1.4 kilogauss also we can say. So the thickness of the sample, it will be 0.2 millimeters, the thickness of the sample. Then what they did is current is changing, the Hall current. That means where the current is passing through the sample, that is Hall current. So that is 1, 1.5, 2, 2.5, 3, 3.5, 4 milliamps. The current is in this direction. Similarly, there is a induced Hall voltage also there, that is a 14 to 57. The variation is 14 millivolts to 57 millivolts. So in that way, so with varying current, voltage also varying. So we can take this initial what we are adjusting the current. So this we will take the in x-axis, that is a current. So this is a induced one. We don't know how much voltage is coming. So that voltage we will take in a y-axis. So for this purpose, this way we will draw the curve, draw the graph. Then it will be, we can like this, the curve will be like this. You can see at 1 milliamp, there is a value will be around 14.378. You can see here around 15. So there is a point, 1 point. So in that way, so there is will be almost straight line. If some data points are in a random, so you don't bother about that. So where the line will be straight line, there you just draw the line, the straight line. Where the more number of points will be in that line, you have to adjust. Okay, so then you just draw the slope. Slope, how we will calculate? The slope is equal to y2 minus y1 by x2 minus x1. So what is y2 here? Y2 means here at the A point, that will be around 72 or 73, minus y1, that is around 25. So in that way, that is we can take it as a 73 minus 50, here it will be 15. 73 minus 15, that is y2 minus y1 divided by x2 minus x1. x2 is this one, that is a 5. x1 is 2.75, 1.75. So that means 5 minus 1.75. So this will be, it will give the slope. So that slope into thickness divided by current. So you will get the divided by magnetic field here, because here current versus voltage graph. So you can see the calculation part, the slope is equal to AB by BC, that is this distance by this distance. Then it will be 9.3 centimeters. That is not a scale one, that is a scale parameters. Okay, so that scale is each centimeter, it will be 5 millivolts. So calculating the in that way, so you will get the slope will be 14.3. So this 14.3 slope, so that is VH by I, this is the slope value. We need another two parameters, that is the thickness of the sample and magnetic field. How much magnetic field we use? That is 0.482 Tesla we are using. The thickness of the sample is 0.2 millimeters. That means 0.0002 millimeters. So in that way, so we are getting around 0.193, that is the Hall coefficient value, that is meter cube per coulomb. This is the Hall coefficient for calculating any type of material, that is semiconductor or insulator. Okay, so these are the references. I took that most of these parameters. Okay, so this reference value, and this experiment, that's Hall effect, is very useful for semiconductor industry, where if you use pentavalent or trivalent, we all know that it may be N type or P type will come, but we don't know exactly how much concentration we are doping. But the doping one is going inside or not, we also don't know exactly. So for that purpose, this Hall effect is very useful to calculate the type of semiconductor, which type of semiconductor it will be. So we are doping some material, that may be, it may be 5 plus or 3 plus. If we forgot that it's 5 plus or 3 plus, so how we can recognize that material? So then this Hall effect is the best method. Otherwise, you have to go to another EPMS, so many hard experiments. But here, if the RH value is negative, then you will get this type of material, we call it as a N type material. If RH value is, that means Hall coefficient is positive, so you can say it will be P type material. And using this Hall coefficient and conductivity, we can calculate the mobility also. Mobility means how the electrons will move inside the material. That also we can calculate using this Hall coefficient. Similarly, the carrier concentration also we can measure using this Hall coefficient. So these are the applications, that major applications are means which type of material it will be. It may be semiconductor, but it is a N type or P type. We can calculate using this one. Similarly, carrier concentration and mobility also we will calculate using this Hall coefficient. Thank you.